and I formulate it as a Poisson problem. And I want to do it by using the cut finite element method. So I have an inner mesh, an outer mesh, and a cut mesh. And the cut mesh is then doubled. And I set up a mean value, a weighted mean value, cleverly weighted to be able to show stability. Okay, so these weights are then in cases where the contrast is not too big. If the contrast is very big, you might want to change these, and you might want to add ghost penalty to the method as well, but this is at least the basic method. It's Nietzsche's method with the averages of the test function, the gradients of the test functions, averages of the normal derivatives of the pressure, and the Nietzsche term. Okay, but I also want to have transport on the interface, flows in the crack. And of course, I have considered other interface conditions than this. Of course, if this is a heat conduction problem, you might want to have the jump in flux equal to something if you want to model heat release on the interface, for instance. If you're solving an elastic problem, you might want to have the jump of the displacements equal to the traction in order to be able to model the cohesive zones. So I've considered that. But what I had never considered was that you might want to solve a differential equation on the interface. Because I had no idea that the concept even existed in this setting. So I was very happy to see this paper by Urshansky, Royskin, and Grande, where they actually only considered the interface. And they formulated differential equations on this cut interface only. So I thought, okay, this is great. Now modeling capabilities are vastly increased. So what they did was they used tangential differential calculus, of which I'd never heard. But it was easy to understand. So you formulate the surface gradient by simply projecting the three-dimensional gradient onto the surface plane, in the tangential plane, using the normal vector to the surface. Then you get three new derivatives, which I call x gamma, y gamma, zeta gamma. And you can set up the surface Jacobian, and you can define the surface divergence, and you go on, and everything is just as normal, only you're on the surface. So a simple model for transport on the interface is that you actually have also a Poisson problem on the interface, driven by the influx or outflux of fluids from the bulk. This model is a very simple one, was proposed in this paper, this recent paper. Notice that weak discontinuities can appear now even if the fluxes are in balance because of this term. Or not if the fluxes are in balance, but if the material parameter doesn't vary across the interface, you can still have weak discontinuities in the derivative. Okay, so a modification of Nietzsche's method for this problem is simply to add this term. Now the interesting thing is that the average here in this term on the interface is reversed. So the weights are reversed. Instead of kappa 1 A1 plus kappa 2 A2, we have the reverse. And this is necessary for consistency with the original problem. Okay. But coming now from a practical point of view, I must admit that this stuff is rather complicated. And everything is getting more complicated in this world. So my dream is to try to do it simpler instead. So let's try something simpler. I embed the crack, and then I simply add this. You must admit this is simple. So all I do is I have a diffusion equation in the bulk, and I add a diffusion equation on the interface. That's it. And the method is continuous. Obviously this cannot be perfect, but I did some experiments because I implemented the other method, of course. So I have this example where I have the same porosity on both sides of the interface. I have pressure here equal to 1, pressure there equal to 0, so it's driven, so it would be a plane if there was no interface. And then I have porosity on the interface which increases with y so that I can have an unsymmetric solution. And then I simply compared on this mesh a discontinuous and a continuous solution. So these are the pressure isomers. So you can see that it's slightly more blurred in the continuous case. Of course, it has to be. But still, I mean, from an engineering accuracy point of view, you could use this if you wanted to optimize, right? So if you look at what happens really is that the gradient cannot have a discontinuity like it has here. So in this case, the velocity inside here is 0 because everything is going along the interface, but you have an overshoot of velocities. But still, if you look at the maximum velocity in the crack and divide by the, for the different method, you take the ratio, you see that it sticks around 1 for quite some time here. So, and the thing is, now, you ask about convergence, of course. Well, because we are not fitted here, of course we lose something. We lose half the power of H gamma here. So this is unavoidable, and this is well known for the case where you have different porosities on each sides of the interface. So this is not unknown, of course. But we notice that if we now refine around the interface, then if we set H gamma equal to H squared, okay, then we have optimal convergence. And in 2 dimensions, this doesn't really matter so much because the number of unknowns scales the same way. In 3 dimensions, okay, it's suboptimal. I give you that. But in 2 dimensions, it's okay. And the thing is, sorry, this is an example with a manufactured solution. So you can see that I actually lose convergence rates. If, on the other hand, I tie the mesh size on the interface to H squares outside, and I measure in the bulk mesh parameter, I get optimal convergence. And, of course, now we can do more complex things, like branching cracks. No problem at all. If you do this with the cut finite element method, of course, you have to consider that you have branching points, and you could have several branching points. So you have to implement this now with elements that have several copies, which of course complicates things. It's not undoable. We're doing it right now, but this is much easier. So here's another problem of the same type. Pressure equal 1 here, pressure equals 0 there. Would be a plane if it wasn't for these cracks. Here is a global refinement, and here is only a local refinement. What we really wanted to do, why I even considered this idea, is that I'm involved in a project where we want to do blood flow. And we want to take MRIs, and we want to extract the arteries, segment it, and then we simply want to put it in a mesh and solve some kind of, I don't know, poroelastic problem. This is simply the same Poisson problem again. But what we really want to do is solve some poroelastic problem and then have the arteries or veins going inside here and have a different model there. But if we have a model where we have velocity pressure in the bulk and in the vein, then it can always be coupled. So that's not a real problem. Okay, does it make sense? What is the trace of a function in 3D on this line? No, it doesn't make sense mathematically, I agree. Of course, if you refine the mesh down to the size of the vein, then you would have to change the model, otherwise it wouldn't work. But this is a very simple problem. What we want to do is we want to check if you restrict the blood flow so that you get necrosis of the cells. That's what we want to do. Now, further developments are developments for elasticity. For elasticity, we can use the same projection operator to construct an in-plane strain operator. You pre and post multiply with a projection operator. This is the standard strain in 3 dimensions. And you get a membrane problem. You have the surface divergence of the surface stress tensor equals to F on gamma, and the surface stress tensor is given by Hooke's law as usual. And what I want to do is I want to add this to the bulk equations to simulate embedded membranes. So if I only have a membrane, then the equations look just like they do in 3 dimensions, only I integrate on the surface and I have surface quantities. If I add the bulk equation, of course, it's the same weak form, only over omega instead, and I have the thickness of the membrane. You could plug it in here if the thickness is varying, and just solve. So you can put in membranes inside an elastic solid to strengthen it. You see that it reacts to this membrane. You could put in several membranes. You could stiffen something with a membrane for in bending, for instance. This is some kind of cantilever beam without stiffening, and here is a circular membrane inserted. You see that it stiffens. It's the same load. You can do superimposed fibers. Here, this is an idea. Instead of doing anisotropic elasticity, which is what engineers do to simulate fiber emulsions, you could simply put in fibers. I'm putting some short fibers in the Gauss points here. I put them vertically here. You see there is no difference in the displacement between the structure without fibers and the structure with the vertical fibers. If I rotate the fibers slightly, this is 45 degrees rotation on the fibers, you see you have a stiffening effect. If I make the fibers horizontal, you have a stronger stiffening effect. Okay. So maybe this is not so much of an improvement to the anisotropic material models that they actually use, because what they do is that they superimpose an elastic model which is a continuum model. I do it discretely here, so I don't know, it's just an option. But what they can't do really, or perhaps they can, but I haven't seen it, it's more difficult at least, is to add beams to the equations. So I'm thinking we have a normal to the beam and we have a tangential vector to the beam, we have a normal displacement and a tangential displacement. And we have a rotation of the vertical fiber. Now in Bernoulli beam theory, the rotation of the vertical fiber is simply the tangential derivative of the normal component. And Hooke's law in one dimension is simply Young's modulus times the strength. So the upshot is that you get the usual, I here is the second moment of inertia, so you get the usual Euler-Bernoulli beam contribution, you get a membrane contribution, and you have the loads over there. Now, if I want to implement that in a standard finite element setting, I would need at least P2 elements, because otherwise this character here would be 0. So, okay, if we have P2 elements, C0 continuous, then we could use a discontinuous Galerkin idea for the beam equation. So you have, this is what we call a continuous discontinuous. So we have discontinuous rotations. So the Nietzsche method works only on the rotations, because the displacement itself is continuous. And then we have sort of the contributions from the membrane, the contribution from the interior of the beams. And these this pH here is simply the intersection points between gamma and the element borders, the bulk element borders. So now we can simply try to put in a beam in the center here. If this was just a membrane, it wouldn't have a stiffening effect because it's in the middle of the beam. But now when I put this beam in the middle of the beam, it actually stiffens. Or I could have trusses giving this similar effect, because if I have trusses sitting here, it will have stiffening. Finally, my final example is beam plate coupling. Now, this is the moment tensor for the Kirchhoff plate. So this is the equation for the Kirchhoff plate. Again, it really requires C1 continuity for conformity, but we can use a discontinuous Galerkin method again. Moments times rotations come up in the Nietzsche terms, and I stabilize with the rotation squared. And here is an example where I put two beams in a cross on a square plate off center so that they do not coincide with mesh lines. So I have small parts here. You could say, isn't this a problem? Yeah, it is a problem if we have only the beams, then we would have to stabilize it. But in my experience, the underlying plate actually stabilizes it, so I have no stabilization terms here at all. Here are beams. This is a simply supported plate, and I've added beams simply supported at the ends. If they are weak, if they are flexible, you see nothing. If they are stiff, you see the effect of the simply supported beams. Then I fix the beams at the end. The plate is still simply supported, and then you see that even the flexible beams actually have a strong effect because they are fixed at these points. And if they are stiff, they have an enormous effect. Okay, that's my talk. Further developments, yeah, we are considering right now shell models, of course. We are considering more advanced models for flows in cracks where you have a separate field for the crack, for instance. And we are considering cohesive zones with membrane action. One open question that I would like to raise is, of course, a difficult problem of dimensional transition. I have something which goes over into a very thin structure. I want to move over to a one-dimensional or two-dimensional object. When do I do it? I know how to do it, but I don't really know when. So this is... Thank you.